Okay, so we are continuing chapter 4. In section 4.3, you learned a lot about linear independent sets, what bases are. If you have a subspace, what vectors would form a basis for a subspace. And you learned about bases for the null space of a matrix and the column space of a matrix. Okay, you learned about that. Those are very common subspaces, the null space and column space. And then in section 4.4, you learned about different coordinate systems and how, we don't always have to use a standard basis, for instance, for the three-dimensional R3 coordinate system, I, J, and K, or in our case, we call it vectors E1, E2, E3. We could have different bases for three-dimensional coordinate system, and those bases might be more convenient depending on what we're working with. So like, for example, they have in figure 3 in section 4.4 examples of unit cells. And the vectors that form the perimeter of the unit cells are more convenient than perhaps standard basis vectors. So there's all kinds of wonderful things that you've been learning in chapter 4. And now we come to the concept of the dimension of a vector space. Okay, so there 9, so like R3, that is a three-dimensional vector space. Okay, why is R3 a three-dimensional vector space? Because you only need 3, because the number of vectors in the basis for R3 is 3. Okay, I mean, if I go to the whiteboard here, okay, so a basis for R3, okay, how many vectors would we need in a basis for R3? How many vectors? Is 2 enough? No, you're going to need 3. That's right, Mikhail. Can you give me 3 vectors that form a basis for R3? 3 very simple ones. Okay. Very good. I like that. Mikhail, good. That's right. So this is called your standard basis. This is the standard basis for R3. Okay. E1, E2, and E3. Those vectors, those set of vectors, form a standard basis. But it's not the only basis, right? It's not the only basis. Suppose you had this 1, 0, 0, 0, 0, 1, and 1, 2, 3. Would that be, would this set of 3 vectors be a basis for R3? Well, what makes a basis? Let's think about what makes a basis. The vectors have to be what? They have to be, what are the conditions for a basis? If you have a space, okay, that's right. These 3 vectors, that's right. Good, Mikhail. These 3 vectors, and I appreciate all responses. These 3 vectors are linearly independent, right? And those vectors also span R3. Now, one way you could show this, right, is you could create a matrix. You could create a matrix A, right? And then you could, for instance, you could see Well, you could do row operations on the matrix, okay, and hold on, I'm thinking about the invertible. I mean, it's mentally, intuitively, it is a basis, but if you wanted to just mathematically sort of take the mathematical, I want to say it the right way, sort of just another way to look at it is you could create the matrix A and row reduce A and see how many pivot positions, and you'll see that you're going to have 3 pivot positions here, okay, if you get that matrix in an echelon form or a reduced echelon form. Okay, so that's one way to do it. And actually, it'd probably be easier to put that second matrix, or that second vector, you know, if you made the second vector, just put it as the third column, and then the third vector, put it as the second column. That should work pretty good, pretty well, I should say. Let me just see here. So if you row reduce this, okay, I mean, when you do the row reduction, you should get a matrix like this: 1, 0, 0, 0, 1, 0, and 0, 0, 1. See? And so you have matrix A, row reduced, 3 pivots. So therefore, by the invertible matrix theorem, the columns of the matrix A form a linearly independent set. Okay, does that make good sense? You know, it's not hard to see that you could do it. All you need to do is, if you did a row operation, make that 2 a 1, or just use the second row, take a multiple of it, add it to the third row to eliminate the 3 here, and take a multiple of the second row and add it to the first row. I guess it'd be negative a half times the second row, add to the first row to eliminate the 1 there. And then you're good to go. You got you're going to have a matrix with 3 pivots in it. Okay, so how many do like doing it that way to test for linear? Now that only works, right, if you have a square matrix, but you know, that's a way to do it. Has anybody done it that way? All right, well, so there are many different bases, but a basis for R cubed, you need to have 3 vectors. Therefore, that's why we call R cubed here it's a 3-dimensional space. Where does that come from? Dimensional space. 3-dimensional space means that a basis for that space contains 3 vectors. 2-dimensional space means a basis for that space basis for that space contains just 2 vectors. Okay, so that's the idea behind n-dimensional spaces. And here they mention that if a vector space has a basis, okay, and you have if you have a set in the vector space that contains, hold on here, maybe I'll highlight it. I'm looking right here at theorem 9. I mean, in practical terms, all that is saying is that you can't, I mean, to have a basis for a vector space, you have a certain number of vectors that are needed. And if you go over those, if you have a set of vectors that includes more than that, you're gonna not have a basis anymore. So like, for instance, if we go back to that example we were looking at here, Okay. Let's say in the first one here, standard basis. Okay, let's say, well, I think I'll just write it out. I'll put it here. So let's say you have 1, 0, 0. See, I like to think of easy examples. 1, 0, 0, 0, 0, no, 0, 1, 0, 0, 0, 1, and then you have the vector 1, 2, 3. Okay, is this here a basis anymore? No, why not? Those four vectors do span R3. Any vector in R3 could be written as a linear combination of those four vectors. Mikhail says the vectors are not linearly independent. The vectors are linearly dependent. Can you tell me why? One vector must be, if these four vectors here are linearly dependent, one of the vectors has to be a linear combination of the other vectors. Okay, good. The fourth vector is a linear combination of the first three vectors. The fourth vector is equal to 1 times the first vector plus 2 times the second vector plus 3 times the third vector. So you can't have, in a basis, you can't, a basis is an efficient spanning set. You can't have more vectors than are needed to have the basis. And that's what that theorem in section 4.5 was talking about. Okay, if I go back to the theorem, that's what that's saying, theorem 9. Okay, are there any questions on that? All right, well, let's keep going. Let's keep rolling through here. Hold on here. Yep, good. I mean, a lot of these are very intuitive, these theorems, but they're intuitive if you think of like the easy examples that I'm sharing with you. Okay, theorem 10 says, okay, if a vector space has a basis of n vectors, then any other basis has to have also n vectors. That makes sense. That makes perfect sense. Let's see. Now, David has a question here. Let me see. David's question. For linear dependence, there were a lot of equivalent statements. Well, for the invertible matrix theorem from section 2.3, there are a lot of equivalent statements, David. That is correct. That is correct. All those statements are equivalent. But you don't utilize all of them to help you with section 4, the chapter 4. You don't need to utilize all of them. But indeed, you're correct on that. So, okay, now let's see here. Let's keep going. Okay, so you have something called DIM of V. DIM of V, what's that about? Let me go down here. So if you have a finite dimensional space, okay, the dimension of the space is written as DIM of V, and it's the number of vectors in a basis for V. Okay, and you can have vector spaces that are not spanned by a finite set. Those would be called infinite dimensional. But infinite dimensional, we're not going to do a whole lot with those right now in this class. Okay, so let's look at a few examples. Examples are always helpful. Okay, so example 1, let me just highlight that all. So example 1 says the standard basis for Rn contains n vectors, so the dimension of Rn equals n. The standard polynomial basis, okay, shows that the dimension of the P sub 2, which is the set of quadratic polynomials, that equals 3. Because any quadratic polynomial, any polynomial of degree 2, can be written as a linear combination of 1, t, and t squared. Okay. Are there any questions on example 1? Okay, let's keep rolling. Let's keep rolling. Okay, example 2 here. Okay, in this example, it says let H be the span of two vectors, V1 and V2. Clearly, they're linearly independent. Then H is the plane studied in example 7. Okay, so I might have to blow that down a little bit. So there is the plane, picture of it to the left. The span of the two vectors is any linear combination of those two linearly independent vectors. That would trace out a plane in space. Okay, it would trace out a plane in space. So let me just see here. I don't know if I can. Nope. Okay, that's fine. So the basis for that space, since it has just two vectors, the dimension of space H is 2. Are there any questions on example 2? Okay. Let's move on to example 3. Example 3, they want you to find the dimension of this subspace. Okay, they write down the vectors that belong in the subspace. They have to obey those constraints that you see. And you can write that space H as a linear combination of the 4 vectors below. Okay, so space H here, let me see, let me go to the whiteboard. Let's just talk about this here. Okay, so space H, here it is. I'm writing the coordinates down. The first is A minus 3B plus 6C. Second coordinate is 5A plus 4D. Third coordinate is B minus 2C minus D. And the fourth coordinate is 5D. Okay. And they're letting A, B, C, and D be real. So, you know, you can take this vector here and you can write it as a linear combination of A times a vector. Well, you can write it as A times a vector plus B times a vector plus C times a vector plus D times a vector. Okay, now what would the vector A be? What are the 4 coordinates there for the vector A? For this example 3 we're looking at from section 4.5. What's the first vector going to be here? It's vector v1. Okay, Marcella, good. That's right. 1, 5, 0, and 0. Okay, what about the second vector? Okay, David, good. -3, 0, 1, 0. Good. All right, what about the third vector? Good, David. Good, Cameron. 6, 0, -2, 0. And the fourth vector, V4? Good, Yasin. 0, 4, -1, and 5. Okay. Now, can we say that the dimension of H equals 4? Can we just say that? Meaning that the vectors V1, V2, V3, and V4 form a basis for our subspace H? Gotta be, take a look at V2 and compare it to V3. What do you notice about V2 and V3? Right, that's right. Good, David. Good, Mikhail. The answer's no here because clearly V3, right, that's right, Mikhail. Well, you know, that's why I'm doing this with y'all. V3 equals -2 times V2. So that means we have linear dependence in the four vectors. So, okay. So well, let me ask you this. So a basis for this space H. Okay, let's say we're going to have V1 in there and V2 in there. Okay, they're clearly linearly independent. We don't need V3, right? Because V3 is a multiple of V2. What about V4? Is V4 in the basis? Is V4 linearly independent of V1 and V2? Absolutely. V1 and V2, those two vectors there, the fourth coordinates are zeros for V1 and V2. V4, the fourth coordinate is a non-zero. So this is a basis. This is a basis, and it's linearly independent. So then what's the dimension of our space H? 3, that's right. Okay, so you have to be a little bit careful on these kind of problems. You have to be a little bit careful, but this is this is the idea behind section 4.5. Okay, are there any questions so far? 4.5, incidentally, that assignment won't be due until Friday because, you know, some of you are getting ready to take your test. And so I didn't want to have any assignment due on Wednesday. Okay, all right. Any questions before we move on? Okay, let's keep moving on here then. Let's go back to that book. Hold on here. I have to, one moment. Okay, so let's see. Okay, so now we're back here to the book. And figure 1 in the book, you have some nice pictures here of sample subspaces of R cubed. They show on the left a one-dimensional subspace of R cubed. Then B in figure 1 is a two-dimensional subspace of R cubed. And then finally, C is a three-dimensional subspace of R cubed. And it's actually the whole space. Let's see, hold on, there was a question here. Oh, I didn't notice that, that's right. A zero-dimensional subspace would just be the, well, you know, I'm not worried about that, to be honest. You know, I'm not worried about that. All right. Right, that's right, that's right. Let's keep going if there are no questions. Theorem 11. This makes sense. It says if you have, let me just go down here. If you have a subspace, if H is a subspace of a vector space, then the dimension of the space H has to be less than or equal to the dimension of the vector space it lives in. It makes sense. A subspace, the dimension of the subspace would have to be less than the space it lives in. All right, and let's keep going a little bit further if there are no questions. Trying to free up a little time for you here for something I want to do. Theorem 12, the basis theorem, basically says if you have a p-dimensional vector space, any linearly independent set of exactly p elements in the vector space is automatically a basis for V. Okay, that's similar to one of the previous theorems we learned. Now, let's see here. Here's something where, oh wait, hold on, did the book disappear? Hold on here, what happened? Let's get it back. Okay, hold on here, there we go. One moment. There we go. So null space and column space, you probably learned this already just from the exercises you've already done. But the dimension of the null space of A is the number of free variables that you have when you solve the matrix equation A times X equals 0. And that's because the free variables are, I mean, the free variables form the coefficients in the span of the vectors that are in the null space. The dimension of the column space is just the number of pivot columns in the matrix A. So, and this is something, how many have kind of noticed this or understand this based on homework you've done? What they're mentioning here. Yeah, it should make pretty good sense based on the practice that you're doing. Okay. And let me see here. Okay, so in example 5, they want you to find the dimensions of the null column space of that matrix. So you get it in reduced echelon form. Okay, and well, hold that thought, Mikhail. There are going to be 3 free variables. So the dimension of the null space of A is 3. But the dimension of the column space of A is 2 because A has 2 pivot columns. It is no accident that the dimension of the column space of A plus the dimension of the null space of A equals the number of columns of the matrix A. That is not an accident. Okay, that's called the rank theorem, which we'll see in section 4.6. Okay. All right, all right. So, a problem like this, like in example 5, for instance, I mean, hopefully it's pretty straightforward. Are there any questions? Who's feeling comfortable with section 4.5? It didn't take us long really to cover it. Give me a thumbs up if you're reasonably comfortable. Okay, Mikhail's reasonably comfortable. Marcella is, Cameron is, David is. Jacob is. All right, great, great. Okay, all right, wonderful. All right, well, let me go ahead and stop the recording then.